Welcome to The Explainer. Today, we're digging into what a single sleepless night really does to your brain. We're talking on a molecular level and how it physically changes the very system that runs your motivation and your focus.
You know the feeling, right? That fuzzy, sluggish mental state after pulling an all-nighter? Your focus is completely shot, you feel irritable, and the world just seems a little off. But what is literally changing inside your brain to cause all that? Well, the effects go way beyond just feeling tired. A single night of lost sleep triggers this massive cascade of changes. Your concentration and memory take a serious hit, your emotions are on a hair trigger, and your immune system weakens. And on top of that, key hormones that regulate stress and hunger get thrown completely out of whack. To find the real source of that brain fog, scientists decided to look deep inside the brain, at a region called the striatum. You can think of it as our central hub for reward and motivation. Using PET scans, which let them track chemical activity, they used a special tracer designed to stick to dopamine receptors. And what they found was the crucial first clue. After a sleepless night, a lot less of this tracer was actually binding in the striatum. So this first finding created a central mystery. What did that reduced tracer binding actually mean? Was the brain getting flooded with dopamine, which was just blocking the tracer? Or were the receptors themselves, the docking stations for dopamine, were they actually vanishing? Let's break down these two possibilities. So here's the puzzle. Was the brain getting swamped with so much extra dopamine that it was physically blocking the tracer from its targets? Or were the targets themselves, the dopamine receptors, actually disappearing? Two very different explanations.
And this idea of downregulation is so important. It's not about changing the amount of signal being sent out, it's about the brain's ability to even hear that signal. A sleepless night might be physically turning down the volume knob on your entire dopamine system. So to solve this mystery, researchers designed this really clever experiment using a very common stimulant, methylphenidate. The logic here is just elegant. See, methylphenidate works by blocking the removal of dopamine from the synapse, which makes it build up. So if sleep deprivation was already causing a dopamine flood, adding methylphenidate on top should amplify that effect like crazy, creating this huge tidal wave of dopamine. But if not, the increase should look pretty much the same in both the rested and the sleep-deprived states.
And you know, there were already some hints pointing in one direction. Earlier studies in rats, where they can directly measure chemical levels in the brain, found that baseline dopamine didn't actually increase after sleep deprivation. This was a pretty big early clue that the whole more dopamine idea might be on thin ice.
Okay, so the experiment was set up, the logic was sound, it was time to get a verdict. What did the human brain scans actually show?
And here it is, the smoking gun. The dopamine increase caused by methylphenidate was the exact same whether the subjects were rested or sleep deprived. There was no tidal wave. This was incredibly powerful evidence suggesting that the problem wasn't a dopamine flood at all. It had to be a change in the receptors themselves. But the results were even more specific than anyone expected. Researchers saw a significant drop in the availability of these key dopamine receptors, specifically the D2 and D3 types. But, and this is the kicker, this change only happened in one part of the striatum, the ventral striatum, a region that's absolutely critical for how we process reward and motivation. This just shows you how precise this effect really is. In two other major parts of the striatum, the caudate and putamen, which are more involved in things like motor control and forming habits, there was no significant change at all. So this wasn't some system-wide shutdown. It was a targeted hit on the brain's core motivation circuit. All right, so we have a specific molecular change in a very specific brain region, but how does turning down this one volume knob lead to that awful, overwhelming brain fog we all know so well? So, just how strong is the link between these disappearing receptors and that brain fog we feel? Well, the answer really comes down to this number, 0.50. That is the correlation coefficient that the researchers found, and it shows a really strong relationship. The more a person's D2 and D3 receptors dropped in their ventral striatum, the sleepier and less alert they actually reported feeling. The volume knob was turned down and they could physically feel the cognitive silence.
This really highlights the crucial difference, right? The brain fog from sleep deprivation comes from having fewer dopamine landing spots. But a stimulant like methylphenidate, it works by flooding the system with so much dopamine that it temporarily overcomes that reduced number of receptors, giving you that short-term boost.
And it's really important to see this in context. This dopamine receptor change is a highly specific, targeted strike on your brain's hardware, and it's happening at the exact same time as these broader systemic changes, like a surge in the stress hormone cortisol and the disruption of hunger hormones that makes you crave junk food.
And as a pretty interesting side note, the study also found that baseline D2 receptor levels were naturally higher in younger subjects, and they decline with age. It just suggests our brain's dopamine system is constantly changing throughout our entire lives.
So, what is the big clinical takeaway from all this? If you had to boil this entire finding down into one single sentence, what would it be?
This right here. This single sentence is the clinical pearl. It connects a specific molecular event, receptor downregulation, in a specific brain region, directly to the symptoms we all experience, like poor concentration and sleepiness. That is the entire story in a nutshell.
And this is where the implications start to get really serious. This isn't just about feeling tired. Other studies have shown that having lower D2 receptor availability in this exact same brain region is a known risk factor for substance use disorders. So this leaves us with a really critical and provocative question. We now know that even one night without sleep physically rewires a key part of our brain's reward and motivation system. What then are the long-term consequences of chronic sleep loss? You have to wonder, how might it be shaping our vulnerability to some of the most challenging disorders of our time,